if we're talking about the Beehive problem from the homework, it's very likely, I think, that the question that we're trying to answer in number 7, and this is the one that causes students the most questions and angst every semester. Notice that the question here is asking something about the rate of change of the distance between the bee and the beehive. And so what we have, the information that we have, is that we have two bees that are flying along two different parameterized curves. And so since we know their travel along these parameterized curves, we know how to determine the velocity vector, we know how to determine the speed. So questions 5 and 6 are fairly straightforward. Question 7 is a little bit more conceptual, so it's asking us to think about how can we quantify the rate of change of the distance of each bee to the hive at the moment in time. And the moment in time it's referring to is time t equals 1 second. So at that instant in time, both of these bees are occupying the same position in space. So they have the same distance to the hive at that point. So the question is, how is their distance to the hive actually changing? So I think if we just annotate this diagram a little bit, that could help to get us started. So the first thing that we have for each bee, right, is that we have a velocity vector that is showing us at that instant in time how their position inside of XYZ space is changing. So that velocity vector would be, I'm going to call it v of t. And depending on which bee that we're looking at, right, it's either going to be the derivative of r1 with respect to time or r2 with respect to time. And those would have been the velocity vectors that you computed in the previous problem, right, back here in problem 6. So rather than clutter up your copy of this problem with that annotation, I'll just scrub that for the moment and just say that that's my velocity vector. Meanwhile, I think there's a couple of keys to unlocking the rest. How would we quantify this vector? So the vector that points from the bee's location to the point that the beehive is located. So how could I compute that? What would be an idea? So if I want a displacement vector that points from the bee to the hive, I just have to take the hive's position, p, and subtract the bee's position, which is the position functions, r of t, r1 of t, r2 of t, depending on which of the bees that we're looking at. And so this we could just write as p minus r of t. And so at every point in time as these bees are flying around, p minus r of t is giving me a vector valued function that describes a displacement from bee to hive. So I'm going to kind of write that in here. Displacement is given by p minus r of t. And so the question that is being asked in this problem is, how is that displacement vector's length changing? So that's the big question here. How is that distance, which is measured by the length of that displacement vector, how is that changing as time evolves at the time t equals 1? So what we need in some way is to measure distance, and distance is the length of that displacement. As length of p minus r of t. Right. And so we're really kind of asking here about that distance's time rate of change. So the time derivative of this distance is what we're trying to figure out. Is it greater than 0 or is it less than 0? So that's the ultimate sort of shape that this problem takes. Now, in order to get to... So you could do this in a very straightforward but messy way by actually doing out p minus r of t and writing that out as a vector valued function, and then taking the magnitude of that thing, so it's going to be the square root of the sum of the squares of the x component function plus the y component function plus the z component function. And then that's going to give you some awful function of t, right, underneath a giant square root, and then take the time derivative of it, and then plug time t equals 1 into your thing, and figure out whether that's positive or negative. This would be the brute force way to do this problem. And certainly, if you want to go that route, I'm not going to stop you, but I will suggest that there is a more elegant way to do this. And a more elegant way to do this might be, and this is maybe the trick that unlocks it a little bit. Instead of looking at the time derivative of the magnitude, we could look at the time derivative of the squared magnitude. Why would that be any better? Well, how do we compute the squared magnitude of any vector? If I just write it in here. P minus r of t. Squared, sorry. So what is another way to compute the squared magnitude of a vector? Let's call it x or something. The squared magnitude of x.
We can dot the vector with itself.
We can dot the vector with itself. Yeah, exactly. And why that is a wonderful thing is that unlocks for us the ability to use the dot product rule in this problem. So it's p minus r of t dot p minus r of t. Right? And so we could do this in a few different ways, but maybe the easiest would be, well, maybe I'll just sort of put that little hint in here. Now apply the dot product rule. Now use the dot product rule. And when you use the dot product rule on this, what's going to happen is that you're going to get an expression that sort of expands out, right? It's going to be the derivative of p minus r of t dotted with p minus r of t plus p minus r of t dotted with the derivative of p minus r of t. And keeping in mind that p here is a constant, when you take that derivative of p minus r of t, that p is just going to drop out, right? And we're going to end up with a derivative of r. And so use the dot product rule, expand this thing out, and write it in terms of, so you're going to have a bunch of r of t's and v of t's in which you're going to plug in t equals 1 because we care about that instant in time. And so use the r of 1's and the r prime of 1's that you found in the previous two questions, numbers 5 and 6. So there is my hint for the Beehive problem, is that doing it brute force is certainly an option, but it's going to be messy and it misses an opportunity to leverage the fact that we have this really nice product rule that works for dot products of vectors, that works for cross products of vectors. And so because all we care about here is whether that rate of change is positive or whether that rate of change is negative. We don't need to know what the specific number of the rate of change is. And the distance, the time derivative of the distance will be positive or negative exactly when the time derivative of the squared distance is positive or negative. So we can get away with putting that square in there, which is nice because then we don't have to deal with the square root as part of our computations. So I just realized that we had a little discussion there that I didn't capture in the video, so I'm just going to say that one more time for the record. So when you do out this dot product, what you end up getting is -2 times the dot product of the velocity vector r prime of t with the displacement vector to the hive, p minus r of t. And so whether this time derivative is positive or negative depends respectively on whether this dot product is negative or positive. So when this dot product is negative, In other words, if the angle between the velocity vector of the bee and the beehive is obtuse, like it is in the original diagram, then that means that the time derivative is going to be positive because the dot product is negative and is getting multiplied by -2. And when that's the case, that obtuse angle here means that the bee is actually getting further away from the hive. The time derivative of the distance squared is increasing. And conversely, if I had a bee that was instead making a acute angle in its velocity vector with the displacement, then this dot product would be positive, and multiplying that by -2, this time derivative would be negative, which means that the bee's distance to the hive would be decreasing. The bee would be getting closer to the hive at that point. So yeah, again, this is the path of least resistance, I think, especially because you already know what r of 1 and r prime of 1 are from the previous two problems. I mean, that's what you were computing in question 5 was r of 1 for both b's, and then in question 6 was v of 1 for both b's. So you already did that work, and so once you do out this time derivative, everything is going to be in terms of r prime of 1 and r of 1, and you can just plug those vectors in and find out what this dot product comes out to be, and then that tells you what is the time derivative. So yeah, every year when I assign the beehive question, we end up having a discussion like this one. So I hope this was helpful.